Okay, so let's introduce the rationale and procedures for permutation test. Consider two independent random samples, x1, x2 all the way up to xn, and y1, y2 all the way up to ym. So we have n samples from the distribution fx and m samples from the distribution fy. Let Z be the set which contains both the x samples and the y samples. Also, the Z set is ordered. So we order it as follows. Z is equal to the set with x1 all the way up to xn, and then y1 all the way up to ym. And the set Z can be indexed by new, which is the set 1 all the way up to n, and then n plus 1, n plus 2 all the way up to n plus n. In other words, the ith element of Z is going to be equal to the ith element of X if I is between 1 and n. Otherwise, if I is between n plus 1 and n plus m, then the ith element of Z is the I minus 1 element of Y. Now let's consider the permutation of Z. Let Z star be Y star, X star and Y star. And this is a partition of the pooled sample X union Y. This can be obtained as follows. Here, Z star corresponds to a permutation pi of the integers nu. So the ith element of Z star is going to be the pi ith element of Z. So pi is a permutation function and it's applied to each of the integer indices in the set nu. Essentially, we just shuffle the observations or the indices. After we obtain the permuted Z star, we can set X star to be equal to the first n elements in Z star. And correspondingly, Y star will correspond to the last m elements in Z star. If we let large n equals n plus m, the number of possible distinct partitions of Z, so the number of ways that we can split the set Z into two sets, a set of size m x star, and then the remainders of size m from denoted y star. So the number of possible distinct partitions of Z is equal to the number of unordered ways we can form X star. So since we know Z, once we know X star, we know that Y star is simply the remaining samples, in other words, the complement. Then we know that the total number of ways we can form X star is equal to large n choose small n, and that's given by n factorial divided by small n factorial times m factorial. So let's consider a toy example. Suppose we have two samples of data. So we have our x's, 1, 0, and -1. And then we have our y's. We have two y samples, 4 and 7. In this case, n is equal to 3 and m is equal to 2. That's just simply the number of samples from x and y. And Z is going to be the set. I'm missing the braces here. Z is the set 1, 0, -1, 4, and 7. Since there are a total of 5 elements, we know that the index set nu is going to be just 1, 2, 3, 4, 5. So we can see that the number of possible permutations of Z is equal to 5 factorial, and that's 120. So that's the number of ways that we can permute the index set nu. But we can see that many of them will result in the same partitions of Z into X star and Y star. For example, the following 3 partitions are equivalent because we are considering unordered sets. The first one the permutation is the identity permutation. So we don't do a permutation. So pi applied to new 1, 2, 3, 4, 5 is going to be 1, 2, 3, 4, 5. So nothing has changed. In this case, x star is going to be equal to 1, 0, negative 1, and y star is 4, 7, exactly the same as our original observations. Second kind of permutation we can do is pi of new equals 2, 1, 3, 4, 5. So we shuffle 2 and 1. In this case, we end up with x star is equal to x2, x1, x3. So 0, 1, negative 1. And y star is 4, 5, so it doesn't change. It's still 4 and 7. We can see that this one is equivalent to the first one because the x star is the same if we do not consider the ordering of the elements. Similarly, if we do pi new equals 1, 2, 3, 5, 4, in other words, we shuffle 4 and 5, then we end up with x star equals 1, 0, negative 1, and y star equals 7 and 4. And we still form the same partition because the elements are the same. In other words, not all of these permutations of new will result in distinct partitions of the data. And the number of distinct partitions is given by 5, choose 3 in this case. So here are all of the possible distinct partitions of Z. Let's denote it by Z star equals X star and Y star. And the number of distinct partitions is 5, choose 3. So large n choose small n, and that's equal to 10. Here's just a list of all of the possible distinct partitions. So each row is one possibility. We have the first one, so that's the same as our original observation, so without any permutation. And then the second one is, you can see it's x star given by negative 1, 0, 4, and y star given by 1 and 7, etc. So these are the possible ways that we can split the 5 elements into x star and y star without actually resulting in duplicate sets. So why are we doing this? Why are we doing permutations and combinations again? Well, suppose we're testing the null hypothesis x0, where fx is equal to fy. Then one thing we might consider is how likely is it to observe each partition. This is a place where we are going to introduce a definition called permutation distribution. Let's let theta hat xy be a statistic. So theta hat is a statistic that's computed based on the x samples and y samples, or we can write it equivalently as theta hat function applied to our z's, which is x concatenated by y, and then nu, which is the index set. So theta hat is a statistic. The permutation distribution of theta hat star, a random variable, is the distribution of the replicates theta hat star, which is the distribution of the theta hats applied to Z and a permutation of nu. And we consider all possible permutations that will result in distinct partitions of X and Y. So we know J indexes from 1 to, sorry, there's a typo here. So this should be n factorial divided by n factorial and n factorial instead. I flipped the numerator and denominator. So because there are a total of large n to small n partitions, We know that the J's, the permutations that will result in the distinct partitions, will index from 1 to n choose n. So essentially this is the set where we calculate theta hat, the statistic, on each possible partition of Z into X star and Y star. Okay. So what is the null distribution of theta hat star? Intuitively, under the null hypothesis, where fx is equal to fy, we are assuming that x and y have the same distribution. In other words, in this case, our samples, x1 all the way up to xn and y1 all the way up to ym, are essentially samples from the same distribution because fx is not really different from xy. So let's denote this common same distribution by f, which is equal to fx and equal to fy. Then essentially, no matter how we partition the data, the distribution of theta hat computed with x star and y star should remain the same. This is because no matter how you partition the data, the first m elements, which you denote by x star, is going to be just a total of n samples from the distribution f. And then the remaining m elements are just samples from the distribution f as well. So no matter how you do this, the resulting distribution of theta hat should remain the same. In other words, for any j, so possible distinct partition of z, theta hat j, which is the theta hat function evaluated at z and the permutation pi j applied to nu, has probability 1 over n choose n, which is equal to n factorial times m factorial divided by n factorial. So each of these possible partitions have the same possibility. So it's a discrete uniform distribution. In this case, the CDF of theta hat star is given by f theta hat star t, and that's equal to the probability that a random variable theta hat star is less than or equal to a constant t. And that is simply the 1 over n choose n, so n factorial times m factorial divided by large n factorial times the sum over all j's from 1 to n choose n of the indicator evaluating whether theta hat j is less than or equal to t. This should look kind of familiar to you because this is the same as our empirical distribution, so our empirical CDF. Once we have the CDF of the theta hat star, the permutation distribution, then we can start performing hypothesis testing using permutation test. Let's let theta hat denote the statistic computed from the original observed sample. So theta hat is computed with theta hat function evaluated at z and nu, which is the observed test statistic before permuting the data. So the partition is still x and y, the originals, not x star or y star. Then if theta hat is applied to test H0 and large values of theta hat are considered significant, then the achieved significance level of the observed statistic is given by the probability that the random variable theta hat star is larger than or equal to the observed theta hat. And that's simply, we plug in theta hat into the CDF. So actually is 1 minus this thing. So we also flip the greater than equal to or less than or equal to. But essentially this is plugging in theta hat into t over here. So This actually provides us a p-value that can be used for hypothesis testing. It tells us that under the null distribution, how likely is it for us to observe a theta hat star as extreme or more extreme, or larger than or equal to the observed theta hat. So this formula is for the case where we are doing a one-sided test. So when large values of theta hat are considered significant. You can generalize the idea, and it's going to be quite similar if you want to test the lower tau or for the two tau cases. So if, say, small values of theta hat are significant, you simply flipped the larger than or equal to into less than or equal to here. So this provides a p-value for hypothesis testing. Essentially what this is the probability of observing a theta hat star as large or as small or as extreme or larger or smaller or more extreme than the observed theta hat under the null hypothesis. So let's summarize the procedures for the permutation test. The first step is to compute the observed test statistic, which is theta hat evaluated at x and y. So we also write it as theta hat evaluated at z and nu. This is the statistic computed from the original sample without any shuffling. Second, for each distinct partition indexed by j equals 1 all the way up to n choose n, so n factorial divided by n factorial times n factorial, we compute the statistic theta hat j, which is the theta hat statistic or the theta hat function applied to z and a permutation of nu. So it's essentially applying it to x star and y star where they are permuted. In the third step, we compute the p-value. So let's consider the case where large values of theta hat support the alternative hypothesis. So we do the one-sided test and see what is the chance of getting a theta hat star larger than or equal to the observed theta hat under the null. So the p-value is given by the probability that theta hat star is larger than or equal to the observed theta hat, which we obtained from the first step. And that's equal to what we have displayed before. So it's exactly the same as the formula before. And once we have the p-value, we can reject the null hypothesis at the significant level alpha if the observed p-value is less than or equal to alpha. Say if our alpha is 0.05 and our p is say 0.03, then we reject the null. So we have one problem here. As you can see, indexing and finding out all of the possible partitions of Z involves combinations and some combinatorics. And when n, which is the sum of n and m, the sample sizes gets large, computing theta hat j for each possible partition is going to be computationally infeasible. So when your n is large, then n choose some number is going to be very large as well. And you don't want to spend a ton of computation power trying to index all the possible permutations. In this case, instead of indexing and exhausting all of the possible partitions, we will use Monte Carlo approximation. We only need to do some slight modifications of the previous procedures. Step 1 is going to be the same, where we compute the observed test statistic using the unpermuted or the original samples we have. In step 2, instead of indexing and computing theta hat j for each possible partition, we will do a total of large B Monte Carlo replications. So for each Monte Carlo replication small b between 1 and large B, we will first generate a random permutation pi b of nu. And then this will allow us to partition z into x star and y star. So the first and the elements are x star, and then the remainders are y star. Using this random permutation, we compute the statistic theta hat b, which is the theta hat function calculated at z, and the permutation pi b evaluated to nu. So essentially theta hat applied to this particular partition x star and y star. Then we compute the p-value estimate. Because we are using Monte Carlo techniques over here, the resulting p is going to be an estimate. So like before, we considered a case where large values of theta hat support the alternative hypothesis. Then we can compute the empirical p-value, p hat, an estimate, which is given by 1 over large p plus 1 times 1 plus the sum from 1 to b of the indicator, whether theta hat b is larger than or equal to the observed theta hat using the observed sample, unpermuted sample. So you can see that when we're using Monte Carlo approximation, we're making some slight modifications to the formula for calculating the p. The denominator now has a plus 1 term, and we also have a plus 1 here. Otherwise, everything is quite similar. And then we will reject the null hypothesis at the significance level alpha if p hat is less than or equal to alpha. One question you might ask is, what is a sufficient b? So how many Monte Carlo replications do I need to do permutation test? The textbook has recommended a b that's larger than or equal to 99 and less than or equal to 999. So I think these numbers 99 and 999 are chosen so that the denominator b plus 1 will be something that looks like 100 or 1000.